Okay, we're starting. Still a bit under the weather, but I want to finish limits today, so let's try to just get through it. We're going to talk about one important application of limits, and this is the idea of continuity. We're on the verge of getting into the meat of calculus. We'll actually start talking about that on Friday. But it turns out that we can only do calculus on functions where there are continuous. So I thought I'll talk about what it means for a function to be continuous and how we can actually determine whether it is so or not. And it turns out that we use limits in order to do this. So intuitively, so this is not the strict definition. This is just kind of what you can think of as a continuous function, which is probably what you're thinking anyway, but I just actually want to write that down. The function is continuous on an interval. And of course, this is only true for things that you can draw in the xy plane. If you go to higher dimensions, this is probably not a very good thing to say. But for Calc 1, it's okay. On an interval, if you can draw it without lifting your pencil off the page. That's the intuitive kind of thing, right? Which means there are like no gaps, no holes, no kind of weird behaviors that you kind of have to avoid. The function is just kind of nice and just keeps running along. Everything is smooth. So that's kind of what's happening. Okay, so you're on some interval, say AB, and your function is just doing this thing where you can just draw it without lifting your pencil on the page. And so, for example, if there's a hole, it's not continuous. Or if there's like a gap, it's not continuous. Or if there's something that's called a jump, like that, then it's not continuous. Okay, so you have to be able to draw it without lifting your pencil off the page. And so now, you have a question?
Yeah. Can a piecewise function be continuous?
A piecewise function can be continuous if the pieces actually connect to each other, right? So we have done examples where we had a piecewise function do this, and then it jumped here and did that. Well, if I had defined it so that this line was down here and connected, then it would be continuous, right? So it is possible, right? But that's the idea. If you can kind of draw it without lifting your pencil off the page in the xy plane, that we call that continuous. And yes, all sorts of functions can be continuous, even piecewise ones. But we do need, but drawing is not always very efficient. So we do need actually some other way to be able to tell when something is continuous. I'm just giving you some examples here. Continuous on so I can have A, B, and it's just some function that's doing whatever. But it's doing it in this continuous way. If you look at something that's not continuous, there are multiple ways you can think of something that's not being continuous. And this is kind of going to lead into my definition of continuity. You can have a hole in the function. That's one way for something to not be continuous. You have to lift your pencil off the page to avoid moving into that point. Remember our function that was like x squared minus 1 divided by x minus 1 was a function similar to this. you could have what's called a jump discontinuity. So there's like a vertical jump. And that's not continuous because you have to lift your pencil off the page to be able to draw that. You could have an asymptote or a gap. So let's say here, something like this. Right? Or you can even think of 1 over x squared, you know, if you're around the y-axis, that there's a gap here. That function is in 2 distinct parts. Right? It's split in 2 parts. It's not continuous around the 0. Okay? So anytime there's like a hole or a jump or a gap, that kind of makes something not continuous. And so basically, what we want is a way to identify when behaviors like this happen. When do you get a hole? When do you get a gap? When do you get a jump? And it turns out you can do that with limits. So here's the definition. F of x is continuous. And I think I asked this in the bonus as well, just for you to write down this definition. Is continuous at x equals a, bonus for the test yesterday. If the limit, this is what you have to write down, as x approaches a of f of x is equal to f of a. Note, 3 things need to happen. One, your f must be defined at a. Right, so there must be some value to f of a, right? F of a must make sense, it must give us a number, it must give us an output. 2, the limit as x approaches a must exist. And 3, these guys have to actually coincide. 1 and 2. If those 3 things happen together, then it turns out you'll always be able to draw it without lifting your pencil off the page in that region. What if one of these don't happen? Well, here's an example. If you have somebody with a hole, this is an example of where the limit exists, but f undefined. Right? If you're going from the right hand or the left hand at the point A, you can actually get a limit. Both hands will agree and you will actually get an answer, but the function itself doesn't exist there. You'd end up with a hole, so that would actually work that way. There's also possible for the function to exist at A, like it has an output, which is that shaded point, but the limit doesn't exist. So this is a case where the limit does not exist, but f is defined. So you could have that. You could have cases where f is not defined and the limit does not exist. That would be in a case where you have like a hole like that. So here limit does not exist. F not defined. So you can have situations like this happening. However, once your limit exists at the point A, right? Meaning you're coming from the left and the right side and they give you the same answer. And at the same time, the function output is exactly that answer is the same as well. Here's where the limit exists. F is defined. And they are equal. So in that case, everything is just one fluid smooth, continuous motion. Limits are existing. Anything that might have been a gap is filled in. Everything is nice. You can draw it without lifting your pencil off the paper. So this is kind of the standard here. This is what it means to be continuous. And you can actually talk about that in terms of limits and what the function is at that point. Any questions? There's another definition. F is called continuous if it is. So last time I defined continuity at a point, there was continuous at the point x equals a, but now I'm talking about continuous in general. There are functions that are continuous in general. And these are functions where this kind of behavior happens at all points in their domain. And if you have such a function, it's called a continuous function. Okay? So that definition I gave you only works at a single point. You're just taking a limit at a single point. But if you can do that for literally every single point in their domain and it all works out, we call that a continuous function. There are common ones that we will care about. That means that these are guys that we can do calculus with, usually, and we don't have to actually worry about whether or not we can do it, because we know as long as we're within the domain, calculus will work here. So one is polynomials, of course. You know that polynomials are, actually they're continuous everywhere. There are no back points. Right? So their domain is actually everywhere, so they're continuous everywhere. Rational functions. So we can do calculus on rational functions. And these guys are continuous where the denominator is not equal to 0, right? Because that's where their domain is not working. We can do it on radical functions. They're continuous where they are defined. So again, remember radicals, it really breaks into two parts. It depends on if it's an even radical or an odd radical. Yeah, those are just some nice functions. Let's actually do an example. So exponentials and logarithms. We already spoke about those two. So exponentials, those are continuous everywhere because their domain is everywhere. And logs. Find the indicated limits and determine where f is continuous. broken lines are just for you to be able to read the numbers. So then here's an example of a function. Can you see where the function is not continuous? Like at what x values? Yeah. 3? Okay, yeah. Here there's obviously a big gap. I can't actually draw that without lifting my pencil off the page. So I would think that when this is all said and done, I would be able to identify 3 as a point where we're not continuous. What else? Yeah. 8? Well, by the way, these are negatives. Negative 8, there's a hole here, so that it shouldn't be continuous there. Yeah? 4, there's a hole here, sure.
6.
Well, 6, there's a jump here. So to be able to draw this, I would have to bring my I'd have to lift my pencil up and come down here. So that's actually not continuous. So 6 also. 0. And 0, there's a hole here. Right, so we can actually look at the picture and tell, right? But let's say we really want to examine this for using the limits because we don't want to actually rely on drawing all the time because that's actually too bad. So here's how we're going to examine it. And in general, this is kind of how you're going to want to approach the situation. So I'm going to ask you to determine whether a function is continuous or not. And you're really going to go through and check the numbers, right? You're not going to just say, oh, I can draw it without lifting my pencil, right? So let's say we're going to do it minus 10. Let's say this goes on forever like that. Okay. So here are the numbers. We're going to look at the limit as x approaches minus 10 from the left of your function. Limit as x approaches minus 10 from the right of your function. We're going to then talk about the limit as x approaches minus 10 of the function. Yeah, and there then need more space. Then you're going to talk about the limit. Then you're going to talk about what if the function is defined at minus 10. And from that, you'll be able to conclude whether it's continuous or not continuous. So we're going to go through that process with all these numbers that you see here. Okay. So what about this guy? What's the limit as we approach minus 10 from the left of our function? Because we're coming from the left, remember what the limit is? It's just us looking at the y value. The y value is 1. So that limit is actually 1. And what about the right? Approach minus 10 from the right. The y value we're approaching is again 1. So that's also 1. Here, our left and right hand limits agree, which means that this guy is 1. It's going to be the same as the left and the right hand limits. Now, if I were to look at what the function is actually defined as, well, this is filled in here. So that's also filled in at 1. Literally everyone is returning you the value 1, both the limits and the function. And so you can say, yes, it is continuous here. So you can say it is continuous at 10. Let me just throw in something for emphasis here. Put in a dot over there. This is lining right above that hole. And lining up with this guy. do the same thing for at x equals 8. Minus 8. So we're going to look at the limit as x approaches minus 8 from the left, limit as x approaches minus 8 from the right. Look at the limit as x approaches 8, minus 8. And we're going to look at the function defined at 8, minus 8. And then we're going to make our conclusion. What's this guy? Yeah? It's 1. This guy? Also 1. So this guy? It's 1. So the limit exists and it's actually 1. What is this guy?
Undefined.
It's not undefined. Huh? It's 3. So that's what this is here. Right? When my x is minus 8, it fills in the point with y value 3. So here the limit is not equal to f of minus. The limit as x approaches minus 8 is not equal to f of minus 8, even though it's defined. So it's not continuous. And you can kind of go through and do this for everyone. So if I were to do this at x equals minus 6, we talk about the limit as x approaches minus 6 on the left, limit as x approaches minus 6 on the right, limit as x approaches minus 6. We talk about the function if it's defined at minus 6, and then we can actually conclude whether it's continuous. So minus 6, as we're approaching from the left, we get the value 3. We're approaching from the right, we get the value 3, which means that the limit is 3 because the left and right hand agree that it's 3. And then if I look at minus 6, that's filled in, that's 3. So this is continuous. At x equals minus 6. We'll talk about minus 3. Limit as x approaches minus 3 from the left of the function is going to be negative infinity. Limit as x approaches minus 3 from the right of the function is going to also be negative infinity. It's going down in both directions, which means that the limit as x approaches minus 3 of the function is minus infinity. What is the value of the function at minus 3? Well, it's undefined because there's an asymptote here. So this implies not continuous. And you can do the same thing for all these guys. So we can talk about the limit as x approaches 0 from the left, limit as x approaches 0 from the right. This exercise was to do it so often that you just got bored and it was so easy for you to be able to see it and do it. But me having the flu is kind of like not making me in the mood for this. So you approach 0 from the left, 3, 0 from the right, that's also 3, so the limit is 3, f of 0 is undefined. So here it's not continuous. The 2 is also kind of clear. Both the left and right limits will match up, and the function is filled in here. 4 is very similar to, like, 4 is actually very similar to 0. This one might be a little bit interesting. Let's actually do 6. limit as x approaches 6 from the left, limit as x approaches 6 from the right. So we can talk about the limit as x approaches 6. We can also talk about the function evaluated at 6. What's my limit as I approach from the left? 3. What about the right? 2. What does that mean for the limit? The limit does not exist. So technically we could even stop there, but let's just continue. If I plug in x equals 6 though, that does give me an output that gives me the output 3. But at the end of the day, it's still not continuous. But once either the limit doesn't exist or the function is undefined, you don't even have to do anything further. You don't have to do anything further once you realize that one of those two things happen. But if everyone gives you a value, all the values have to agree and they're continuous. I say perhaps here because there are examples of functions at points where they are continuous, where calculus still does not work. And I'll talk about exampple like that after we talk about derivatives. But if it's not continuous, then you can't even ask the question. Like, it's clear that it's not going to work. But continuity is a necessary condition. Probably not sufficient. So continuity is necessary. Not sufficient. For calculus. So for calculus to even work and be a thing, our functions have to be nicely behaved in some way. But there are there are instances where even when it's nicely behaved in that way, we still won't be able to do calculus, and those situations I will describe to you at a later point. There are about 4 of them. There are 4 situations where even if your function is continuous, calculus is not going to work. And I'll tell you what those are when they come. I also want to talk about a couple more limits. Give these guys some examples. Hear your ideas on how to solve them. limits are very special limits in disguise, but let's see. Yeah.
0 or 6?
It's a 0. These are both 0. Any ideas for the first one? What do you guys think? Yeah?
Is the first one infinity?
Why do you say that?
Because you can't plug in the 0 because it'd be undefined.
Sure.
So once you start plugging in numbers that get closer and closer to 0, you would get. Oh wait, there's a negative side. I only did one side, but
Yeah.
that probably doesn't look good.
So what was our limit strategy again when faced with a new limit that looks weird? There were a bunch of things we actually did. The first thing was to actually try to plug in the number, right? Which obviously doesn't work here. What was the second thing?
Cancel.
Huh?
Cancel.
Try to simplify and cancel stuff. So is there a way to simplify this guy? Is there? Yeah?
You turn the square root of 4% into parentheses and 4% to the patterns and stuff.
So right, this has the 1/2 power. It's not really simplifying, it's rewriting it, but does it give you any ideas if you look at it that way? Or? Because we have simplified guys like this before. I don't know if it was exactly this guy, but something very similar. What if it was the opposite? I just want someone to kind of give me an idea. What would you have done then?
Conjugate.
The conjugate, right? You can do the same thing here, right? So we've actually done guys like this before. 4 plus x minus 2 all over x. So one thing you see this, you realize you can't plug in the number, but now you want to think about how can I simplify. But you realize that you have a sum of terms, and one of them has a radical. You can obviously want to try to get rid of that radical. So what you can do is multiply and divide by the conjugate. You try to rationalize the numerator so you can hopefully turn it into something that can cancel this x. So we can multiply and divide by 4 plus x plus 2. 4 plus x plus 2. So let's actually see what that gives us. So in the numerator, we have this times that, which is like your a minus b times your a plus b, and we know that gives us a squared plus b squared. A squared minus b squared. So we have that in the top, and in the bottom we have this. Now you realize that this 4 and that 2 squared are going to cancel. And we would have x over x times 4 plus x. the x's. So what's the answer?
4.
It's actually a quarter. Like that was kind of weird. Ideas for the second one? Just kind of emphasizing here that you need to remember all your simplification techniques for some of these problems that could show up. Because limits are going to be a big part of the next test, so you need to be able to do a variety of them. You need to remember all your techniques like conjugating, rationalizing. You don't use those all the time, but they're still important to remember. Yeah?
We multiply both the top and bottom by x plus 1.
Right, so you look at all the denominators, right? So the LCD here, realize that the LCD is just x plus 1. So you're going to multiply top and bottom by x plus 1. So this guy is going to multiply, distribute. When you multiply this, they just cancel, you get 1. Minus, in parentheses, you get x plus 1. You multiply that over. Here you have x times x plus 1. So here this is 1 minus x minus 1 when you expand those brackets, so the 1s are going to die and you just have minus x. And so now here we can cancel the x. So this is minus 1 for x plus 1. So now we can put in 0, so that's just negative. Yeah, we'll stop there. That's what we wanted to talk about limits in general. But we're going to do a new application with them on Friday. It's going to be a very important application. See you guys then. So the homework for 2.2 is finally due at this point. And with all those techniques that we learned, you should be able to do that.